Hello students, we are going to review the energetics and thermodynamics consolidation exercise 1, and it is my hope that through this particular review you will have a clearer picture on how to go about constructing an energy cycle as well as the energy level diagram. Okay, you will notice that for this particular consolidation exercise, right, it begins with definitions of key terms. Okay, so if you take a look at it, there are a total of 15, if not 14 energetics term you need to be aware of. Yeah, of course some of the terms are repeated, like for example the first ionization energy. Okay, so you can look at it as like a repeat from a generic definition of ionization energy, and of course the first and second electron affinity. Yep, and of course some of the terms are missing. For example, the enthalpy change of vaporization, the enthalpy change of sublimation, the enthalpy change of fusion. All this you might be familiar with them from physics. Yeah, but for the purpose of H2 we do not require you to define these terms. Yeah, but of course if you know them, it will help a lot in navigating through the questions. Yeah, but whenever these terms are required for assessment purposes, they will be explained to you. Okay, yeah, so without further ado, I will just jump straight into the energy cycle work examples. Okay, so you notice that the work examples tends to be repeated, so the same questions is repeated again. The purpose of doing that is really to get you familiar with the energetics terms and how to go about drawing a cycle. Yeah, and I often emphasize to the students that it is important for you to know the definition before even attempting these questions, because if you don't know the definition, it is near to impossible for you to get the correct cycle. Okay, yeah, so for question 1, you are given this particular reaction. Okay, so you need not actually know what kind of reaction this is, because this is not important at this stage. Okay, so you are given the enthalpy change of formation of each compound. Okay, so they are listed here. Then your job is to calculate the enthalpy change of the reaction using an energy cycle. Okay, yeah, so what I'm going to do now is I'm just going to rewrite the equation. Okay, so I'm going to have 4 CH3 and H and H2, and then this is in the liquid phase. Do take note that the state symbols for energetics experiments as well as related questions are very important, because the defined values is related to the states the compounds are at. Okay, so plus 5 and 2O4 in the liquid phase, and then I'm going to get 4 CO2 gas plus 9 N2 gas, and then plus 12 H2O liquids. Okay, yeah, so what I'm going to do now is, because we are given the enthalpy change of formation of each of the compounds. Okay, so I'm just going to write in red. Okay, so we're given this, we're given this, we're given CO2, we're given H2O. Okay, you notice that nitrogen is not given. Why is that the case? Well, if you look at the fundamental definition for the enthalpy change of formation, it is the enthalpy change when 1 mole of the said substance is formed from its constituent elements. So the constituent elements of dinitrogen is dinitrogen. Yeah, so in that case, the enthalpy change of formation will be 0, because pretty much you are going just from nitrogen to nitrogen, yeah, by definition. Okay, so that's why you're not given the enthalpy change of formation for nitrogen. Yeah, and quite a number of students have the misconception that the enthalpy change of formation of dinitrogen is the bond energy. For some reason, they have that misconception. And I'm also a little bit puzzled why that is the case. But definitely that is not the case. That is not the definition, so don't get confused. Okay, yeah, so I'm just going to remove the arrows, the ticks. Okay, then I'm going to draw in the cycles. Okay, so I'm going to draw in blue. Okay, so I'm going to define the enthalpy change of formation for CH3, NH, NH2, 4 of it. So I'm going to count the total number of carbon will be 4 carbon. Okay, so that's in the solid phase. Okay, plus how many hydrogen? So that's 2, 3. 3 plus 3 is 6, and then 6 times 4 is 12. So that will be 12 H2 gas. Okay, and then after that, I'm going to add up the nitrogen. So that's N plus N. That's 1 N2 and then 4 N2 in total. So 4 N2 gas here. Okay, that's pretty much about it. And remember the coefficients. Yeah, so coefficient is very important. So there are 4 of it. Yeah, 4 in total. Okay, so what we need to do is to multiply this by 4. Okay, so do take note of this. So I'm going to take 4 times 53. Okay, and next I'm just going to write in red for clarity. Okay, to define the enthalpy change of formation for N2O4. So that would be 5 N2 gas, and then plus 10 O2 gas. Okay, yeah, so I'm going to write in red, right? So if I write in red here, so maybe I'll change this to red. Yeah, you'll make it a little bit clearer. Okay, so that I think with the coloring, it's a little bit clearer. I could highlight as well, but in this case I choose to write in different color. Yeah, so in this case I am defining the enthalpy change of formation for N2O4. Yeah, so in that case the value will be 5 multiplied by minus 20. Okay, yeah, so do take note that the mass should be conserved. So there must be material balance. Material balance in what sense? There should be material balance over here. Okay, as well as material balance over here. Okay, so left to right there must be balance, and then from the bottom right to the top left over here must be balance as well. Okay, so do take note of that when you're constructing the cycle. Yep, and of course here will be balanced. Yeah. Okay, yeah, so what I'm going to do now is I'm going to just close up the loop. Remember that the most important idea of an energy cycle is that the loop must be closed. It must be a closed loop. If you have an open loop, then your cycle is not complete. Okay, yeah, so we have 4 CO2. So where do we get the 4 CO2? I'm going to highlight. So the 4C is here, and then I'm going to get 4 O2s from here. Okay, so out of the 10 O2, I'm going to get 4 of it. Okay, so over here I'm defining. So I'm going to get 4 multiplied by minus 394. Okay, and then after that I'm going to define H2O. So I have 12 H2O, I have 12 H2 here, and then earlier on I've used up 4 O2 in the enthalpy change of formation for 4 CO2. So now I'm going to use up the remaining 6. Okay, yeah, and then you notice that it's balanced. Okay, then in that case I'm going to have 12 over here, and then multiplied by minus 242. Okay, and then you notice that the nitrogen, so there are 9 nitrogens in total, but I'm not going to do anything about them, because remember, from nitrogen to nitrogen is actually 0. If you want to, you can write in 0. If not, you can just ignore it. Okay, then after that I'm just going to sum them up. So so therefore the enthalpy change of the reaction, okay, is actually equals to, okay, so remember, how do I go from left to right here? Okay, I'm going to go from left to right by going through an alternative path, because these are all state function. So I'm going to go like this, down and up. Okay, so if it's against the flow of the arrow, yeah, I need to reverse the sign. Okay, so in this case it's minus 4 times 53, and then minus 5 times minus 20, and then I'm going to add up 4 times minus 394, and then 12 times minus 242. Okay, and then I'm going to punch the calculator. I should be able to get minus 4592 kilojoules per mole. Okay, so that will be the final answer for this particular question. Yep. Okay, so it is important for you to take note on a few things. Okay, if I'm a little bit long-winded, you can just skip to question 2. Okay, so what are the things to take note of? I think number 1 is there must be material balance in your equations, and then number 2 is you must take note of the coefficients. Okay, and then of course number 3 is you must ensure that you multiply the coefficient to the respective enthalpy change of formation term. And of course the cycle you have drawn, right, must be a closed loop. Okay, yeah. And then next I'm going to move on to question 2. It's actually a very similar question, but yeah, I'm just going to repeat it in the same thought process. Okay, so what I'm going to do is if you want to, you can work on this, stop the just pause the video. If not, you can continue watching. So I'm going to rewrite the equation for BCl3 liquids plus 3SF4 gas. Okay, and then I'm going to end up with 4BF3 gas plus 3SCl2 gas plus 3Cl2 gas. Okay, so same idea. I'm given the enthalpy change of formation of BCl3, SF4, BF3, SCl2. I do not need the enthalpy change of formation of chlorine because by definition it is 0. Okay, then I'm going to continue drawing the cycle. Okay, so boron is actually an element, solid phase. So 4 boron. Okay, I'm just going to put it in the solid phase. And then altogether 3 times 4, 12 Cl. So that will be 6 Cl2 gas. Okay, so I'm going to define this. The value given to me is negative 427, so that will be 4 multiplied by negative 427. Okay, and then plus formation of SF4. So SF4 is given as minus 775. Sulfur exists as S8. Yeah, so this is kind of like a requirement that you need to know for Cambridge exam. So in this case, I'm going to write it as 3 over 8 S8. But let's say if you forget it, if you forget about it during your assessment, right? It should be fine if you write it as 3S solid. But if you know it, I think it might be better if you write it as S8. Okay, and then of course plus 6F2. 6F2. Okay, and then gas. Okay, over here I'm defining this. Okay, so that will be 3 multiplied by minus 775. Okay, and then I'm going to have BF3. Okay, so it should be balanced. Why? Because I have 4 B's here, and then F3s are all here. Okay, so that's perfect. Okay, so BF3, and then this will be negative 1137 times 4, so that's 4 multiplied by negative 1137. And then SCl2, okay, so SCl2 will be 3 over 8 S8. That will be 3 multiplied by minus 19.7. Okay, and then of course 3 of the Cl2s I'm going to use it from here, and then the remaining 3 will be carried over. Enthalpy change of formation by definition is 0, so that will be fine. Okay, so same thought process. This will be the enthalpy change of the reaction. Okay, so I'm going to write it down here. Enthalpy change of reaction is actually equals to, it goes like this. Okay, against the flow of the arrow, I put a minus sign in front. Okay, so that would be minus 4, minus 427. Okay, and then minus 3, minus 775. Okay, and then plus 4 times minus 1137, and then plus 3 times minus 19.7. Okay, so if I just punch my calculator, I should get minus 574.1 kilojoules per mole. Okay, so that will be how you should be constructing your cycle. And then again, double check your answer by ensuring that the coefficients are balanced, the material is balanced, and it's a closed loop. Okay, yeah. Then next I'm going to move on to drawing another cycle for question 3. Yep, you are required to use the following standard enthalpy change of combustion. Okay, so do take note of what is given to you. You are no longer given the enthalpy change of formation, you are given the enthalpy change of combustion. Okay, so you are given slightly different data to calculate the enthalpy change of formation for ethane. Okay, so I'm going to define the enthalpy change of formation for ethane. Yeah, so that will be 2 carbon solids plus 3 H2 gas. Okay, remember, you need to know your definition. So the enthalpy change of formation for ethane is the enthalpy change when 1 mole of ethane, so that will be C2H6 gas, is formed for its constituent elements. So the constituent elements will be carbon and dihydrogen. Yeah, so C2H6, just put in the necessary coefficients. Okay, you are given the enthalpy change of combustion data. So that involve carbon, hydrogen, and oxygen. So that will mean that I will have to artificially add in oxygen into my equation on both sides in order to balance it. Yeah, but before I do that, maybe let us balance the equation first. So we have 2 carbons. So if I'm going to combust the carbon, I'm going to get 2CO2 gas. Okay, and then of course for hydrogen, 3H2O liquids. Okay, and I'm going to balance the required oxygen here. So altogether, 2 times 2, 4, 4 plus 3, 7. So I will need 7/2 oxygen gas. Okay, so if I add 7/2 oxygen on the right, I will also need to add 7/2 oxygen on the left. Okay, so this is what I'm going to add it in. Okay, so you just need to ensure that they are balanced, and then after that, I'm just going to input the data. So for carbon, that will be 2 times minus 393, and then for hydrogen, that will be 3 and then minus 286. Okay, and then for ethane, that will be minus 1560. Okay, so I need to double check, ensure that the material is balanced. Ensure that the coefficient is multiplied accordingly. So the coefficient is 1, so that's fine. Okay, then ensure that it's a closed loop. So it's a closed loop, then that will be fine. So that will be the enthalpy change of formation of ethane. So I'm going to do the same thing. So that will be enthalpy change of formation of ethane is actually equals to, so again, I'm going to go like this. Okay, so against the flow of the arrow, or is it going with the flow of the arrow? So that will be 2 multiplied by minus 393 plus 3 multiplied by minus 286. Okay, and then minus 1560. Okay, so I'm going to punch my calculator. I'm going to get minus 84 kilojoules per mole. Okay, yeah, so that I hope the thought process is straightforward. Some of the textbook, or even in our notes, or even for some of the online websites, they put the oxygen on the arrow, so that adds to the confusion. Yeah, so my suggestion is put the oxygen as part of your balance equation. That will make your life a lot easier. Okay, we're going to do the same thing for question 4. You notice that question 4 is exactly the same as question 3, except that instead of ethane, we are using hexane. Okay, so because of that, I'm just going to make our life easier by just writing it out quickly. So for hexane, that will be C6H14. Okay, 14 liquids. Okay, and then of course here we are defining enthalpy change of formation. So I will need 6 carbon here, 6 carbon solids, and then plus 7 H2 gas. Okay, and then same logic. If you're going to burn them completely, I'm going to get 6 CO2 gas plus 7 H2O liquids. Okay, then same idea. I'm going to write in the amount of oxygen added. So that will be 6 times 2, 12. 12 plus 7, 19. So that will be 19/2 O2 gas. Okay, I'm going to add it on the right, and then I'm going to add the same amount on the left. Okay, then I'm going to write in the balance equation. Okay, so for combustion of 6 equivalent of carbon, that will be 6 times minus 393. Okay, for the combustion of 7 equivalent of H2, so that will be 7 multiplied by minus 286. Okay, and then for combustion of hexane, that will be negative 4163. And then just ensure that my loop is closed. Okay, so over here I'm defining the enthalpy change of formation of hexane. Okay, I'm just going to write it here because there's no space below. So again, just ensure that the coefficient is correct, just ensure that there's material balance, and then I'm going to go from left to right. Okay, and then if I'm against the flow of the arrow, I need to switch the sign. Along the flow of the arrow, no need to switch. So that will be 6 multiplied by minus 393 plus 7 multiplied by minus 286, and then minus 4163. Okay, so I'm going to punch the calculator. I should be able to get minus 197 kilojoules per mole. Okay, so that will be the enthalpy change of formation of hexane. Okay, and then for question 5, it reads, use the bond energy data from the data booklets to calculate the enthalpy change of formation of hexane. Okay, so this is a slightly different approach. I need to use the data booklet, calculate enthalpy change of formation of hexane. And then we are supposed to account for the difference in values from that obtained in question 4. Okay, so I'm going to flip over my data booklet, but before I do that, I need to be able to draw out hexane. Okay, so hexane actually looks like this. So it's a straight chain hydrocarbon. So the end is a CH3, and then in the middle there are CH2s. So I'm just going to write out all the CH2s. Okay, H, and then H, H, and then CH3s. Okay, and then I need to be able to know how to draw it because I need to count the number of bonds broken. Okay, so I will count the total number of CC bond that I'm going to break. So that will be 1, 2, 3, 4, 5. So I'm going to break 5 CC bonds. Okay, so I'm just going to write it somewhere here, 5 CC. Okay, and then I'm going to count the number of CH bond I'm breaking. That will be quite straightforward. The middle is 4 CH2, so that will be 8. The end are CH3, so that will be 6. So 8 plus 6, that's 14. So 14 CH. Okay, I'm going to write it here for my reference so that it's easier for me to go about working on the problems. Okay, then I'm going to write out again the definition for the enthalpy change of formation of hexane. So that will be 6 carbon solids plus 7H2 gas. Okay, I'm going to end up with C6H14 liquids. Okay, yeah, you notice that I'm given the enthalpy change of atomization for carbon. Yeah, because you know that by definition, bond energy is defined as the amount of energy you need to break 1 mole of covalent bond in the gaseous states, and the bond breakage is homolytic. So meaning that once the bond is broken, if it's a single bond, then each of the fragment will get 1 electron from the pair. Okay, so in this case, I need to ensure to the best of my ability, whatever I get is in the gaseous phase. Yeah, so definitely I will need to atomize the carbon. Okay, so if I atomize the carbon, so I'm just going to work it out first. So that will be 6 times 715. So in this case, I'm going to get 6 carbon gaseous plus 7H2 gas. Okay, and then I'm going to continue to break all the HH bonds. So I'm going to get 6 carbon gaseous plus 14H gaseous. Okay, I'm going to look up the data booklets. So HH covalent bond, the bond energy is 436. So that will be 7 multiplied by 436. Okay, and then I've already counted the number of CC bonds and CH bonds. So I'm going to continue from here. So in this case, I'm going to take 14, okay, multiplied by 410. So that will be the strength of the CH bond, and then 5 multiplied by 350. You notice that I did not convert my hexane into the liquid phase, into the gaseous phase. Yeah, the reason being the enthalpy change of vaporization data is not given to me. Yeah, so in this case, it's just a proxy I'm using that the enthalpy change of vaporization may not take on a very large value, but of course, eventually they did ask us to account for the difference in the values. Yeah, so you can use that as part of your argument. So the enthalpy change of vaporization is not taken into consideration in this particular computation. Okay, so enthalpy change of formation here, I'm going to do the calculation, perform the calculation. So that's formation here. Okay, so that will be 6 times 715 plus 7 multiplied by 436. Okay, minus 14, 410. Okay, minus 5 times 350. Okay, if I punch the calculator, I'll get negative 148 kilojoules per mole. Okay, yeah. So I think there is indeed a difference of about 50 kilojoules per mole. So you can give a few explanation. I think in the lecture notes, usually it's written that the bond energy given in the data booklet are largely average values. This applies to the CC bond energy and the CH bond energy. Yeah, because the one in the data booklets, they are taken from a large library of data. Yeah, so the CH bond energy could differ between compounds. Yeah, so in this case, it's not always 410. It can range from like 300 plus to even like close to 450. Yeah, so it really depends on the nature of the compound you're dealing with. Yeah, but please do not say that the hydrogen bond energy is average value. Okay, yeah, because for hydrogen bond energy, it only applies to the dihydrogen. Yeah, so this is an exact value. Okay, it has been found by researched. Yeah, so for hydrogen, or for those diatomics, or yeah, I mean those with well-defined structure, and we're looking at diatomics in this case, the elements in itself, right? They are definitely the exact values. Okay, unless of course they are bonded to, or they are interacting with some other compounds, but we don't deal with them in our case here. So we assume that we are looking at a system where the dihydrogen is free to roam around, free to move around, and then collide and then give rise to the product. Okay, yeah. Then next we're going to move on to question 6. Okay, here we have dinitrogen pentoxide can be produced from the following reaction sequence. Okay, so first we will need to apply a huge amount of energy, and then to form NO, and then after NO will burn to give us NO2, and then NO2 will react further to give us N2O5. So we are moving away from energy cycle, although we are still doing energy cycle. So we need to draw both energy cycle and energy level diagram to help us determine the enthalpy change of formation for N2O5. Okay, so what we're going to do now is we are just going to define the enthalpy change of formation for N2O5. That might make our life easier. So N2O5 will be N2O5, okay, gas. Okay, so that will be N2 gas plus 5/2O2 gas. Okay, so that will be the enthalpy change of formation for N2O5. Okay, then so we're just going to take it slowly from process 1, 2, and 3. Okay, so first N2 and O2 to give us 2NO. So I'm just going to have 2NO being formed. But you notice that only 1 mole of oxygen is being used. We have 2.5 moles. So I'm left with 3/2 moles of O2. So 3/2 moles of O2. I'm going to write it down. So that will be 180. Okay. Then after that, for NO, right? 1 equivalent NO reacts with half equivalent of O2 to give you 1 equivalence of NO2. But I will be forming 2 NO2 here. Yeah, because I have 2 equivalent of NO. So I'm going to react with 1 equivalent of oxygen. In this case, I'm left with half moles of oxygen. Okay, so this is negative 57. So that will be 2 multiplied by negative 57. Yeah, so this cycle is quite easy to draw. Okay, and then of course 2NO2 plus half O2, and then this is negative 55. Okay, so if I just sum them up, what I'm going to get is enthalpy change of formation will simply be 180 plus 2 times minus 57 minus 55. Okay, so I'm going to punch a calculator. That will be equals to minus 9.0 kilojoules per mole. Yep. With a little bit of the empty space here, I'm just going to draw out a energy level diagram, although I'm not sure whether this can be shown nicely. Okay, so this will be in terms of kilojoules. Sorry, I don't think it shows up very nicely here, so that's kilojoules per mole. Okay, sorry for the bad handwriting here. Okay, then I'm just going to showcase how an energy level diagram can be obtained. Okay, so it usually helps if we can define this. Okay, so that would be the formation enthalpy. Yeah, we don't know if it's positive or negative. Yeah, so in this case, since we've already done the cycle, right, we know that it's positive. So of course, in reality, right, in actual exam, if you don't know if it's positive or negative, actually it doesn't really matter, because if you, let's say you point downwards, because energy level diagram, it really depends. If it's endo, it should point up. Exo, it should point down, right? So if you accidentally point downwards, actually it doesn't really matter. So you do not need to redraw the energy level diagram. Yeah, but in this case, since we know that it is going to be endo, I'm just going to point up. So 5 half O2 gas, I'm just going to point up here. So that would be the enthalpy change of formation. Okay, so that will be N2O5 gas. Okay, so normally it does help to check out what is the largest value. Okay, so that's minus, or rather that's plus 180, right? So this is the largest value. Just going to draw a long arrow, so that's 180. Okay, so that will give me 2NO gas plus the remaining oxygen, 3 half O2 gas. Yep, and then after it just slowly move towards a destination. In this case, these are all exos, so I'm just going to move down. So it's exo, right? Yeah, so I'm gonna I'm left with 2NO2 gas, okay, plus half O2 gas, and then I'm just going to complete the cycle. Okay, but I'm going to write down the value first. I'm going to zoom in a bit. Yeah, so that will be 2 multiplied by minus 57. Okay, and then I'm just going to complete the cycle. So this will be minus 55. Okay, yeah. So this is how I can perform and draw my energy level diagram. Yeah, so in this case, in order for me to go from to find out this, I'm just going to go like this. Okay, so if I'm with the flow of the arrow, that will be positive. Against the flow of the arrow, that will be negative. But there's no against the flow of the arrow because it just goes in one nice loop. Yeah, some of you might be wondering, let's say if I point it in this direction, what's going to happen? Yeah, actually nothing much is going to happen, because eventually you will still end up the same answer with the correct sign. Okay, so you do not need to worry about it. Yeah, because you know, sometimes when we worry too much about it, we might just stare at the questions for a long time, but actually there isn't a need to. You can simply just move on. Yeah, not to worry. Okay, yeah, so I think it comes with a little bit of practice. Probably I mean, you do not need to be too worried that you can't get the answer eventually lah. Yeah, because after you are familiar with the cycles, then you notice that many of the cycles you can just draw them out easily, but it does come with a bit of practice. Okay, then next we are supposed, again, it's similar to question 6 lah. You notice that the question sort of repeat itself a little bit, so that to really get you familiar with how to draw cycles and level like diagram, right? I'm supposed to again calculate the enthalpy change of formation for N2O5, but this time round I'm given different sets of data. Okay, so what I'm going to do now is again I'm going to write down the definition. So that's N2 gas plus 5 half O2 gas. Okay, so this is the enthalpy change of formation for N2O5. So that's N2O5 liquids. Okay, so now I need to check what are the data I'm given. Okay, so you notice that it's very important to recognize this. The most important data is actually this. Yeah, because it involves the products. Yeah, so if it involves the products, right, that means that you have to artificially add in something. Yeah, so that is like maybe a little bit of clue I can share with you guys. Sometimes it's a bit hard to decide if you need to artificially add in a reactant or something. But so you just need to prowl through your data, right? see if it involve any H and like any additional reaction that actually involve the product. If it does, then you need to artificially add in that reagent. Okay, so in this case I need to add H2O, so plus H2O liquids. Yeah, so if I add in one equivalent H2O here, I will also need to add in on the left hand side, so that is plus H2O liquids on the left. Okay, yeah, and because of that, it might be easier if I start my cycle on the right hand side, because that involves the second equation. Okay, so I'll just going to start it, minus 76.6. Okay, so that gives me 2HNO3. Okay, 2HNO3 liquids. Yeah, and then from here I can straight away look at the third equation, because the third equation also involved the production of nitric acid. So that will make my life easier. Maybe I change color to green. Yeah, so 2 equivalent, so that will be 2 multiplied by 174.1. Sorry, that's negative 174.1. I'm going to write everything out, in this case in blue. Okay, so N2 gas plus 3 half O2 gas. Oh, sorry, not 3 half O2. I need to multiply by 2, right? So my apologies. So that will be 3 O2 gas. Okay, 3 O2 gas. Okay, and then plus H2 gas. Okay, and then yeah, then I will produce 2 equivalent of nitric acid. Yeah, and then you notice that this is actually the most fundamental. This is the elemental state, right? Yeah, so in this case I'm going to combust 1 equivalent of H2 to give me H2O liquids. Yeah, and in this case I do not need minus 571.6, because I'm only forming 1 equivalent of H2O, not 2 equivalent. So I'm going to multiply this by half. Okay, minus 571.6. Yeah, and then right now I'm going to complete the cycle. I'm going to draw, not complete the cycle, I'm going to sum everything up. So I'm going to go from left to right like this. Okay, so again, if it's against the flow of the arrow, I need to switch the sign. So enthalpy change of formation, in this case I'm going to use the space here. This actually equals to minus half. Yeah, minus 571.6. Okay, and then plus 2 multiplied by minus 174.1, and then minus 76.6. Okay, and then eventually I'll end up with my plus 14.2 kilojoules per mole. Okay, the answer is quite similar, although it's not the same. The reason is, of course, different sets of data are being used. Yeah, but it should be quite close. I mean, if you calculated something, let's say I'm getting the 100 over, right, that means something is wrong with the data, or maybe there's something wrong with the calculations. Yeah, but of course, for assessment purposes, we will not give you the same set of calculation consecutively involving the same compound, because that really don't quite make sense. Okay, yeah. Then, of course, the next thing you're probably going to do is perhaps to draw out the energy level diagram. Yeah, because in this case I mean, fundamentally everything is about the energy level diagram, right? Yeah, so we are going to look at the data with the largest value. So in this case, again, this is the set of data with the largest value, because enthalpy change of formation of H2O is actually a whopping 571.6. Of course, in this case, it's half of it. Yeah. Okay. So I'm going to again draw the energy level diagram. So that will be energy slash kilojoules per mole. I'm going to write out my 0 points. That involve the elements. So I'm going to write out a long line. So that's N2 gas plus 3O2 gas plus H2 gas. Okay, and then I'm going to go all the way down, which leads to a formation of 1 equivalent of water. Okay, so I'm just going to use a bit of a space here. Okay, so I'm just go all the way down, and this should forms the water. So that I'm left with N2 gas plus 5 over 2 O2 gas plus H2O liquids. Yep, so this will be half multiplied by minus 571.6. Okay, and then of course at the same time, I'm going to form two equivalent of nitric acid. Yep. To make my life easier, I need to sort of determine which value is bigger lah. Is it half times 571.6 or is it 2 times 174.1? Yeah, you can either do mental sum or you can just sum them up quickly. So if you wish to do that, yeah, just punch your calculator and then you will sort of notice that okay, the nitric acid is found slightly below that of N2, 5 half O2 and H2O. Okay, so I'm just going to write out the nitric acid. So that's 2 HNO3 liquids. Yeah, and then I'm going to end up with 2 multiplied by minus 174.1. Okay, and then of course, sorry, HNO3. This is not very clear. HNO3. Okay, and now of course the nitric acid. How am I going to define the enthalpy change of formation for N2O5? Of course, over here we calculated it to be positive, right? But let's say you don't know, right? So you don't know where to place it. It could be placed either here or it could be placed either here. Yeah. So actually, as I mentioned to you, it doesn't really matter where you place it because eventually you'll still end up with the same answer. Okay. Yeah. So I'm going to place it just slightly above. Yeah. That's really because earlier on we did the calculation. Of course, for assessment purposes, let's say you really don't know, then really don't bother yourself by trying to decide whether is it up or down. Yeah, just draw in something. Yeah, so this gas plus H2O liquid. Yeah, so I'm going to go up. This is the enthalpy change of formation. Okay, and then of course over here, right, we have the hydrolysis of N2O5. Yeah, so to give us nitric acid, so that's minus 76.6. Yep. So again, how am I going to sum up my cycle? This is what I should do. This is my eventual goal, right? So I'm going to go up and then go down and then up. Yeah. So if I go against the flow of the arrow, I must add a negative sign. Okay. Same direction as the arrow. I will keep it, and then against the direction of the arrow, then I will switch the sign. Okay, so eventually I'll end up with the same answer. That's 14.2 kilojoules per mole. Alright, yeah, so I hope after working through some problem, you'll find that it's not as difficult as it seems. Yeah. Alright, so moving on to the Born-Haber cycle, which tends to be easier. Born-Haber cycle is just an energy level diagram for ionic compounds. Yeah, I mean the name is like very, it seems to be quite different from the usual the usual kind of cycles, but it's actually the same. It's just an energy level diagram for ionic compounds. Okay, so we're supposed to use a Born-Haber cycle or rather to construct one involving magnesium oxide. So in this case, we don't need a cycle. We don't need to draw an energy cycle, but we need to draw an energy level diagram involving magnesium oxide, and then calculate the enthalpy change of formation for MgO. Yep. So normally I share with my students that for ionic compound, it's really very easy. It's much easier than for this kind of random compounds, because for ionic compounds the cycle is quite standard. I'm just going to showcase to you why is it very standard. Okay, so this is energy, okay, in kilojoules per mole. Okay, so I'm going to draw a line down. Okay, so first of all, right, the easiest is to, because we need to define the enthalpy change of formation for magnesium oxide. So we need to start with a 0 point. Oh, earlier on I forgot to write in the 0, so the 0 should be here. So this is the 0 point. Yeah, but normally this is probably a lot more important for the energy or for the Born-Haber cycle. Okay, so I'm going to define Mg. Okay, so maybe I should write a bit lower. Mg solids plus half O2 gas. Okay, so I'm defining this. This is the enthalpy change of formation for magnesium oxide. So this will be MgO solids. Yep. Okay, so now normally for Born-Haber cycle, right, you are always given a lot of data like atomization, EA. You are not given ionization energy data because they can be found in the data booklets for most of the compounds they ask you to sketch lah. If you can't find them, then you need to look for alternative sources, or rather it will be provided for you lah. Yeah, and then sometimes you are not given the atomization enthalpy for your for things that you need. The reason is because you can actually use the bond energy data to help you lah. Yeah, so for example, just a random example I can think of lah. So for example, the Cl covalent bond, right, is 246 kilojoules per mole. So if you break one equivalent of Cl covalent bonds, you are going to get two equivalent of chlorine. So this is bond energy, 246 kilojoules per mole. Yeah, so essentially this is the enthalpy change of atomization for chlorine times 2. Why is it the enthalpy change or atomization of chlorine times 2? Because enthalpy change or atomization, let me move up here to the definition page, right, is defined as the enthalpy change when 1 mole of gaseous atoms, okay, in this case gaseous chlorine atoms, is formed when energy is applied to, in this case, because I am atomizing an element, so energy is applied to the element itself. So the definition is related to 1 mole of gaseous atoms produced from its elements. Yeah, so in this case, if I just input the bond energy value for chlorine, I'm producing 2 equivalent of chlorine atoms. Yeah, so in this case, the enthalpy change or atomization of chlorine is simply its bond energy divided by 2 or multiplied by half. Yeah, so sometimes the data are not given, but you can use your data booklet's bond energy data. Yeah. Then what is the simplest way for us to draw the Born-Haber cycle? Well, the simplest way is really check out the lattice energy, because it will usually be the one with the largest magnitude. Remember earlier on I mentioned the trick to drawing energy level diagram is to locate the one with the largest magnitudes. Okay, so in this case, you'll be very, very high up. Okay, very, very high up. And then Mg2 plus gaseous plus O2 minus gaseous. Okay, so you go all the way down, and then this is minus 3889. Yep, so your job, to put it in the simplest way, your job is to move all the way here. Yeah. So Born-Haber cycle is easy because of this. Because it's easy to check how to, it's visually very simple because I just need to move from the elements to the gaseous ions. Yeah, so that makes it a lot easier as compared to a random energy level diagram for a random reaction. Yeah, so basically you just need to be meticulous and systematic. Okay, so now I'm going to use maybe green to help us navigate through. Some of the common mistake would be students tend to forget to atomize the magnesium or the metal. Okay, you must remember to atomize the metal, so that will be 150. Okay, and of course we are not given the atomization for oxygen, right? Yeah, it is perfectly okay because we just need to look up the data booklets and go and find out the bond energy of dioxygen, so that's 496. And then I just need to multiply it by half. Okay, because I'm only producing 1 equivalent of oxygen atom, gaseous oxygen atom. So that's Mg gaseous plus O gaseous. Okay, and then what I'm going to do right now is I'm going to move all the way up. I'm going to release 2 electrons. So that will be first and second IE. So look at the data booklet, that's 736 plus 1450. First and second IE of magnesium. So that will be Mg2 plus gaseous plus 2 electron plus O gaseous. Okay, and then after that I'm going to move down because the first electron affinity of oxygen is negative. Okay, so that's negative, so that's minus 142. Okay, so that will be Mg2 plus gaseous plus electron plus O minus gaseous. And then after that, the next one is plus 798. Okay, so that's 798. Okay, yep. So remember to check the coefficient, but for MgO it's quite straightforward because the coefficient are all 1, so it's a lot easier. Yep. And then after that, what I'm going to do now is I need to find out this, right? Okay, so I'm going to move like this, like this, like this, and like this. Okay, so against the flow of the arrow, switch the sign. Okay, go with the flow of the arrow, no need to switch the sign. Okay, so enthalpy change of formation of MgO. Okay, so that will be equals to 150 plus 496 times half plus 736 plus 1450. Okay, again, and then after that minus 142 minus 798. So you notice it's all in the same direction of the arrow. Yeah, so that's very, very straightforward. So negative 338.89. Okay, so again, everything else is very, very straightforward. So you can easily determine the just compute them. Make sure you compute them properly. Sometimes students read 69 as 96, 68 as 86 for some reason, but just make sure you compute them properly. You should be able to get negative 649 kilojoules per mole. Okay, so please check out. Right, okay. Then if you make some mistakes, you can go back and recalculate. If not, you can move on to the last question, which is something like a synoptic question, because we also combine some chemical bonding. Okay, so for hydrazine, okay, so hydrazine, again, I think we mentioned this quite often. Draw the Lewis structure. So Lewis structure for hydrazine, N2H4. You can simply start with the dot and cross diagram if you wish. You know that nitrogen is able to form 3 single bonds. So if you do a dot and cross, it will be quite straightforward. HH, and then after that dot cross N, and then of course there will be cross 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 dot H cross dot H. Okay, so it looks like ammonia, but it's not quite ammonia. Basically, every H in ammonia replaced by an H2. So that's hydrazine. So dot and cross diagram is like that. Of course, for the Lewis structure, you have to remember to showcase the lone pairs of electrons in the central atom. Okay, something like this. You do not need to show the shape, but I just purposely draw it in to make it look nicer. Okay, then next I need to write out a chemical equation to represent the enthalpy change of formation for gaseous hydrazine. Okay, so hydrazine will be gaseous, so that's N2H4 gaseous. Yep, so that will involve 1 equivalent of dinitrogen and 2 equivalents of dihydrogen. Okay, so this is defining the enthalpy change of formation of gaseous hydrazine. Yep, then use the bond energy data from the data booklet, calculate the enthalpy change of formation. Okay, so I'll need the bond energy data. Okay, if I wish to, I can actually create a cycle based on this. Okay, so so that we apply what we have learned. Okay, so I'm going to look up the energy bond and energy data. So for nitrogen, it's 944 kilojoules per mole for the triple bond. So I'm going to get 2N gaseous plus 2H2 gaseous, and then for hydrogen, that's 436. Okay, so that's 2 times 436. Okay, so I'm going to end up with 2N gaseous plus 4H gaseous. Okay, and then after that, what I'm going to do now is I'm going to calculate the number of N bond I'm going to break. So that's 1, so that's 160, and then and the number of NH bond, that 1, 2, 3, 4, that's 4 multiplied by 390. Okay, yeah, so I'm going to use the same logic, go like this. Okay, so in that case, enthalpy change of formation is simply 944 plus 2 times 436 minus 160, okay, and then minus 4 times 390. Okay, so I'll end up with plus 96 kilojoules per mole after punching the calculator. Alright, so I hope that's fine with you. Right, okay, so next for part D, given that the enthalpy change of combustion, so I'm given the combustion data, okay, is negative 622 kilojoules per mole, and formation of water is negative 286. Calculate enthalpy change of formation for liquid hydrazine. Take note that earlier on is gaseous hydrazine, now it's liquid hydrazine. Okay, so I need to combust liquid hydrazine above. Okay, so I'm going to use a little bit of space here, so that will be N2H4 for liquids formation. Okay, so sorry, not formation, combustion, so plus O2. Okay, gas. Okay, the thermodynamic stable states, probably I'm not going to expect NO2 to be formed. I think number one is I'm not given any data for formation of NO2, right? So in this case, I'm just going to assume that I'm just going to end up with N2 over here. Yeah, of course, it is possible for NO2 to be formed, but it really depends on the condition. Okay, and then of course plus 2H2O liquids, and then this will be negative 622. Okay, so that's given to me, right? And then over here, I'm going to define the enthalpy change of formation for liquid hydrazine. Okay, so liquid hydrazine is like here, so that's N2 gas plus 2H2 gas. Okay, I need to find this, so this is formation. I need to find out what it is, and then of course I also have some oxygen left behind. Okay, because it gets carried over, so I'm going to highlight the oxygen over here, right? And then after that, I'm going to close the loop because I'm given the enthalpy change of formation for liquid water, so that's negative 286 multiplied by 2. So after writing out the balance equation as well as the data I require, I'm just going to define the formation enthalpy in this direction, okay, in this particular direction. So I'm going to go from over here in anti-clockwise fashion like this. Okay, so therefore the enthalpy change of formation will be negative 286 multiplied by 2 minus 622. Okay, because the direction involving the combustion of N2H4 is in the opposite direction. Yeah, so I'm just going to punch the calculator. I'm going to end up with plus 50 kilojoules per mole. Okay, yeah. So I hope this will be relatively straightforward for you to perform the calculation, and then again for you to review how to draw an energy cycle. And then finally, hence calculate the enthalpy change of vaporization for liquid hydrazine. Okay, so this can be easy or it can be difficult. It really depends on how you look at it. Okay, so perhaps let us define the enthalpy change of vaporization for liquid hydrazine. So of course that involves N2H4 liquids to give us N2H4 gas. Okay, so this is the enthalpy change of vaporization of liquid hydrazine. Okay, then actually what data are we provided with, or what are the data available? The data available is the calculated data from part C and D. That is the enthalpy change of formation for gaseous hydrazine. Okay, so we know this. Okay, then we also know enthalpy change of formation of liquid hydrazine. Okay, so since we know these data, then our life will be a lot easier because that will be N2 gas plus 2H2. Okay, gas, and then sorry. And then we are just going to input the values in. What have we calculated? Let me check. Yeah, so this is actually plus 50. Yeah, so this is 50. Okay, and then for the other one is 96, which is here. Okay, so in order to determine the enthalpy change of vaporization, we just need to go like this. Okay, so that will be equals to minus 50 plus 96. So that will be equals to plus 46 kilojoules per mole. Okay, of course you can also you don't really have to use the cycle to help you solve this. Some of you can straight away get it off the top of your head, and then just plug in the values to be minus 50 plus 96. Yeah, if you can do that, that is fine also. Okay, so I just hope that this particular review helps you to understand a little bit more of how to construct a proper energy cycle to solve energetics problem. Okay, so I hope you enjoy the review. If you have not subscribed to the channel, please do so. Thank you.